This is an introduction to general navigation so that it helps you know where to start. And I'm going to go over a small number of topics. We're going to start with looking at Gen Nav as a subject, where it comes from, why it's not really a navigation subject for a start. That's actually a really helpful thing to understand. It's not got a huge amount to do with actual navigation. Then we'll look at where you are at PPL level. So anyone integrated watching this might be a little behind this, but those doing a modular course, they should be at PPL level navigation, and I accept you've probably forgotten quite a lot of what you learned in the theory, but you probably do know actually how to navigate an aircraft and get to where you were intending to go. And that will encompass things like great circles. We'll look at at the moment you use this VFR map, and they're all pretty much, well, they're all very similar, the maps you use, whether they're UK ones, UK quarter mil, UK half mil, or some of the overseas ones. In essence, they're very similar. And then we'll look at how we're going to what we're going to do with the flight computer that you've not done with the flight computer before, and why the flight computer you're using is possibly more advanced than the one you started with on PPL. So the pulleys line up. You've got the CRP1, which is often used for PPL, and now the CRP5, which is not only larger, it has a couple of extra functions. And we will use it differently. What are the functions that you can do on the CRP1, but you didn't? We will look at some. We will mention some of those. Then I'll take a quick look at Form of the Earth, really just because it's probably the first thing you need to learn. Yeah, it is in my early videos, but a quick sketch over and some of the formulas. Now, the reason I want to mention these is because partly actually feeds into item 1 here. So general navigation as a subject. And one of the big problems of Gen Nav as a subject is it's very, I would say it's very coherent in a lot of ways. So when I'm teaching you topic A, we start to bring in topic B, which we haven't learnt yet. The problem is if I then taught you topic B first, well, then there's probably something, maybe bits of A come into that, or possibly even bits of C. And so it happens a little in other subjects, but not so much as Gen Nav, that there's no ideal order in which to teach the subject. Whatever order we teach the subject, I will be mentioning things we haven't done yet, and connecting things in with new subjects. And a classic example is a lot of courses will teach Earth convergence. That's one of the formulas I'm going to talk about later, Earth convergence. And then later on bring in chart convergence. But actually, Earth convergence is a lot more easy to understand if you bring in chart convergence at the same time. But then the problem is you don't know about the charts. You don't know enough about the charts to understand chart convergence until you brought in the charts. But then that gets more complicated still. So really, ideally, I would want to teach about half the subject in one lesson. And just teach it all together because it's always coherent. Now, that will inevitably be a problem. It's one of the reasons, by the way, that I prefer paper books, is that at that point, if you feel you need to look something up that's not been taught yet, either when you're watching a video or when you're reading your books, you can flick through to the next page. Well, yeah, I mean, that's the, I mean, in terms of, I very rarely read paper books anymore. So I'm a real fan of electronic information. But when you're learning something for the first time, because of largely because of this, the ability to flick through, I prefer a paper form. So if you've got PDF books, try and get some printed in certain subjects. I know I've worked with students who have literally printed their PDFs out just for their own satisfaction, so they can then do that. Okay, so it is a very coherent subject. However, it's coherent in something completely wrong. Now, for a start, it is not really navigation. Okay, so general nav is not represent. Let's say, put a bit more formal, not representative of air navigation as experienced, as you will experience when you're flying. Okay, so you have two other subjects. So flight planning, that tells you how to use the actual charts you're likely to be using with IFR navigation and VFR navigation, of course, because you've got the ED4. So that's the Jefferson version. They're not great charts, but they're acceptable. And you'll practically use them. You'll look at the information. You'll extract the information from those charts. You will use them in the way that you will for real flying. You will obviously for the IFR work, you'll just look at the information on there and extract it. For the VFR, you'll draw lines on the charts and measure the lines. And now, yes, you'll do that to some degree in GenNav, but that's a very small part of general navigation. It's the actual practical writing on a chart. And in that case, when you are writing on a chart, you're probably writing on an IFR chart. And I'm one of the few people you'll encounter who's ever actually done that for real. When I was flying a Seneca with no inbuilt GPS late at night, so I got a like 250-mile direct, and therefore had to start plotting my position to work out, to check my navigation to confirm I was going in the right direction, because I couldn't obviously I couldn't receive the VOR near the place I was going to, so I had to actually do, on a couple of occasions I've had to actually do real plotting, but that's not a thing you regularly do in real life, and it's not a thing you're likely ever to do in real life, in fact. So flight planning looks at that in much more the same way. And then on the VFR side of it, in GenNav, as far as I know, they might not, I'm not sure they even touch the VFR chart. Flight planning is the subject that looks at the practicalities of IFR and VFR navigation using the charts and extracting the information from that. And then, of course, radio navigation tells you not only how the navigation equipment works that you'll use for, obviously, most of your career will be IFR navigation or instrument navigation, but it does tell you how you use it as well, and what displays there's quite a lot of emphasis on what displays you're expecting from the radio navigation equipment. So these two subjects are the real navigation subjects. So that if they're navigation, what's GenNav? GenNav is a maths exam. Primarily geometry, not just geometry though. So it's a maths exam. To the degree that I was working with a student on other subjects who didn't need any help with GenNav, because his father, who had a maths degree but no experience, no connection with aviation at all, had taught him everything he needed to know about GenNav. So it's all you need. Maths is all you need to know for GenNav. Now, of course, that's going to frighten some people and make them nervous. But in UK terms, it's bare GCSE level maths. It's not advanced maths. And even to that degree, there are only a handful of questions where they make you do any real, what I would think of as real maths, even on that level, i.e. trigonometry, where you actually have to work out what trigonometric formula you're going to use. I've literally maybe one or two questions where usually, yes, we use the trigonometric functions, sine and cosine particularly, but they're in formulas that you're going to know. Yeah, and so the level you should be at, the thing I really try to work with my students on the math side is that you don't do any real, what I would call real math in the exam. I reduce it to what I call poking a calculator. Yeah. So you've got a formula, you write out what that formula is, and then you plug it into it. You write down the numbers that are in the formula. Maybe the worst you should have to do is rearrange the formula for the most part, and then just plug those numbers into a calculator. Now, if anyone's struggling with rearranging formulas, there's a couple of maths videos on the YouTube channel, and I think on the Subscribe Star channel as well, which will help you with that. For rearranging formulas, the short one's better. The second one, I did go over that, but not as well. I went over a bit more stuff, but the short, it's about half-hour video or so, which goes through the basics of trigonometry and rearranging formulas, so basic algebra to the level you need. And even then, even the algebra in the rearranging formulas, they're nearly all of the formula of the form x equals y over z, or x. Let's rearrange that. So, or y equals x times z, which actually obviously that's the same formula. They're all you remember them all as one of these two forms, yeah. And of course that can be done with the triangle method. So x equals y over z, and easily rearranged. So you don't have to really, even there, you don't have to do any proper algebra. You can do all the shortcuts and mnemonics. So when I say GenNav is maths, that's a warning that you should approach it as if it was maths, and not quite forget the navigation implications, because all the examples are examples from navigation, of course. It's just, if you treat them too much as navigation, you'll approach them, I think, the wrong way, and because this isn't how we navigate aircraft. Right, so that's the biggest thing about the nature of the subject. The second thing is about the history of the Royal Air Force, strangely enough. And it's, if you go back to the 1960s, the Royal Air Force had the British nuclear deterrence, and that moved to the Royal Navy in 69, I think. And so what happened is all the crews flying the Vulcans and the Victors, a load of them were made redundant, including my father was a Vulcan pilot. And back in the late 90s, of course, those same people were coming to the end of their careers, they were reaching retirement. In fact, my dad went into semi-retirement around that time. Now, of course, a lot of the navigators from that fleet had moved on into the CAA because they weren't pilots, but they did know about aviation, so they could work in the CAA, and more generally into the aviation training system. So a lot of the UK trainers were, particularly in the navigation field, were ex-Vulcan and Victor navigators. And I had a lot of people in training me over the years who were ex-Vulcan and Victor navigators. And the problem is, of course, GenNav was a subject that was under the UK remit in the late 90s. Each subject was actually issued to a country to sort of manage the subject when the original JAR exams were coming in. And so these people were in charge of it, and they learnt navigation from the old World War II navigators. Back in the late 50s, early 60s, the ex-World War II navigators were teaching them. So suddenly everything makes a lot more sense if you realize that what you're doing, or at least half of what you're doing or more, is World War II navigation. Yeah, RAF World War II navigation. Hence things like direct Mercator, which feeds on to having to do conversion angle. The conversion angle is completely meaningless unless you're going to use direct Mercator charts effectively. And departure, again, likewise, it's kind of meaningless unless you're using direct Mercator charts. Not entirely, but not particularly useful. And then there's things like multi-drift wind calculations. So there's a calculation you do on the flight computer where you know the aircraft drift in two different headings, or 2 or 3 headings. That we used 2 in the exam. Back in the war they used 3, which meant you could work out the wind without knowing the ground speed, because when they were going over to bomb Germany, they could find out their drift using the bomb site, but they couldn't find out the ground speed very accurately. So they would take the drift on 3 different headings, and then they find the wind, which would make navigation a lot easier. And so this is, if you approach it as being this type of navigation, well, it explains to a large degree why we're using conversion angles and departures. Yeah, they're not really anything to do with modern navigation. That feeds back into the direct Mercator chart, which is a chart we'll mention in a minute, which is completely obsolete for almost all purposes. Yeah, you'll use it in MET, actually, strangely enough. A load of the MET, high-level MET charts and the significant weather charts are direct Mercator. But apart from that, unless you're flying regularly very near the equator, you're not going to use a direct Mercator chart for much at all. Right, so that's the nature of GenNav. Okay, so now we're going to look at where you are and going into ATPL. And I mentioned first great circles there. So for long-range navigation, the great circle is important because a great circle arc is that's the shortest distance between 2 points on a spherical surface. Now, we haven't formed with the Earth yet. I say these whole subjects to be taught together, right? Yes. When we mention form of the Earth, we'll see the Earth isn't quite a sphere. But for all our calculations, we're going to assume the Earth is a sphere. Yeah. Otherwise, a great circle doesn't exist, by the way. Yeah, there are no great circles on the surface of the Earth because the Earth isn't a sphere. And a great circle is defined on a sphere. But anyway, the arc of a great circle is the shortest distance between. So an arc is a segment of a circle. It's a part of the circle. It's the shortest distance between 2 points on the surface of a sphere. It's the closest thing we can get to a straight line. On a flat surface, the shortest distance between 2 points is a straight line. Okay, but on a sphere, it's a great circle arc. So the great circle comes into long-range navigation, and the really important thing about a great circle is it doesn't have a constant bearing. So what you've always assumed when you've drawn a straight line on a chart, which is not quite a great circle, but it's pretty close approximation, particularly on the UK VFR charts. They're very accurate locally. That's very close to a great circle. But you've probably been told to measure it in the middle when you do measure it. Over the ranges you're flying in light aircraft, it probably doesn't really matter. But the reason you're told to measure it in the middle is that the bearing changes very slightly. When you measure it in the middle, that's the average bearing, which would also be the rhumb line bearing. We mentioned rhumb lines earlier. So the rhumb line is a line with a constant bearing, and that follows a slightly different path. And as we get longer and longer ranges, the difference between the two gets greater and greater. And so for short ranges, we'll just approximate our straight line on the chart to something with a constant bearing because it's very close approximation it does. But once we get to long range, we have to understand how the bearing of a great circle arc changes. So that's a big change we're going to go into, which feeds into the formulas you need to know, and particularly into two of the formulas we're going to talk about briefly at the end. Okay, so that's one of the big changes onto ATPL level. Okay, so the next one, VFR maps to all charts. So you only ever use one chart, and it's such a small range that effectively we can say things like north is up. But we're going to be looking at charts where true north is any direction on the chart. So you're going to look at, for example, the polar stereographic chart, which is accurate in the polar region. Now, of course, in the North Polar region, true north is always towards the North Pole. And in the South Polar region, it's always away from the South Pole. And so depending on where you look on the chart, if we map the polar region, true north is going to be in any sorts of directions. And so we're going to have to account for that when we're moving from using a small segment chart, like just southern Britain or Northern French chart I've used once or twice. And obviously on those charts, effectively north, it's not directly up. You'll see, obviously, most people have seen that the meridians converge towards the north. So the meridians, which represent north, you've been assuming that so far, but probably hasn't been explicitly explained to you. But the meridians, where you measure true north off, they point slightly towards each other, up towards the north. If we're in the southern hemisphere, if we were learning this in South Africa, they'd obviously point slightly towards each other towards the south. But as a basic thing, north is up. Yeah, it won't be exactly on all the charts, and even on some of the moderate size charts, it will be changing enough to matter more. And that feeds back into, again, we're having to learn the same thing. We're having to learn all in one. That feeds back into our great circle. That's why if we draw a straight line on a chart, which is not quite a great circle, but is approximately a great circle, another thing you need to know is that the straight line on the chart isn't exactly a great circle. It is close. That's why the great circle is changing, because that north keeps changing. So even if we draw a straight line on a chart and want to follow that straight line, because north is changing, the bearing of that line is changing. Yeah, and so we're also going to have to consider that the scale changes slightly. Now, it's a little artificial for the ATPL exam because of the Mercator chart. Now, the Mercator chart is accurate and scale varies less than 1% if you stay within about 8 degrees of the equator. So within about 500 miles of the equator. So about 8 north to 8 south, somewhere like that. Then the scale varies less than 1%. But for exam purposes, they'll look at the chart at wildly different locations. And at 60 north, the chart scale is twice what it is at the equator for a Mercator chart. and you need to know formulas for that. So we need to consider that the chart scale is changing. And fundamentally, it must. We can't map the surface of the Earth onto a flat surface. In fact, for exactly the reason I've already mentioned, again, bringing in the currents of the subject, we've already said that the shortest distance between 2 points is a great circle. Well, on our map, it's a straight line. And they don't quite, we can't get them to exactly map to each other. Yeah. It's something called non-Euclidean geometry. So what you learned at school was the geometry of flat, I think that's how you spell it. Anyone who knows me knows I can't spell, but anyway. Euclidean geometry. That's the geometry of flat surfaces. And so, for example, you learned that the angles of a triangle add up to 180 degrees. Yeah. But now, if you replace our straight lines with great circle arcs, which we know are the shortest distance between 2 points, if I draw 3 lines from the North Pole to the equator if I draw the Greenwich meridian down to the equator, from the North Pole down to the equator, I then draw around the equator to 90 east. Yeah. And then I draw back up to the North Pole. What I've drawn is 3 great circle arcs. And so I've drawn a big triangle. But the 3 angles in that triangle are all 90 degrees. That's a real right angle triangle. So what you can see is that the angles of the triangle add up to more than 180, in this case 270. But on any spherical surface, the angles of the triangle are going to add up to more than 180 degrees. And so clearly, if that's the case, we can't make a perfect chart or a map that perfectly represents the surface of the Earth. Because obviously I can't draw a triangle with 3 right angles on a flat surface. So what we're using is non-Euclidean geometry. And that means that nothing on the Earth maps perfectly to the map. So we're going to have to learn some of the approximations and some of the conversions, yeah, and some of the differences. And so but none of this mattered at the scale of Southern Britain, say. So you take the UK Southern Britain half mil chart, which I've got myself somewhere, not a particularly big chart, not a particularly wide area. It's approximately a flat surface. If you look at a globe, that's approximately a flat surface. And so it maps very well, very, very closely. But once we get to larger areas, we're going to have to see where they differ. Okay, so that's a big change from the PPL level navigation. And the final one I'm mentioning here, particularly just out of interest, is the extra things we're going to be doing on the flight computer. So we'll look a little at conversions, unit conversions, which you probably didn't do many of, but you might have learned. But there'll be more of them. Yeah, there's more variety. Now, you may want to do all your unit conversions on the calculator if you know the factors. Some people do. But I always teach the backup on the flight computer, just in case you forget the conversion factors. Because even if you just use the flight computer, then to remind you what the conversion factor was, and then you use your calculator. Yeah. But really, on the circular slide rule side, so on that side of the flight computer, the numeric, the one with the numbers around the circle, which is a circular slide rule, the main difference is going to be compressibility correction. So and Mach numbers. So you're going to do TAS to Mach calculations, or indeed Mach to TAS. Yeah. but you're also going to do CAS to TAS, probably not the other way because that gets slightly confusing, which will be shown in the video, I think, but potentially the other way, but probably not. With greater than 300 knots TAS. Now, the point about greater than 300 knots TAS from the point of view of the flight computer is that means there's compressibility. Yeah, the air compresses, so there is a correction to be made for the compressibility correction, which can be done on the flight computer, or there's apparently all the questions now have a numerical compressibility. So if you are using a flight computer without the compressibility correction, you can use the number. Use the number because it's quicker and more precise. That's the main change on that side of the flight computer. You might also look at the altimetry, so the temperature correction for altimeter. To be honest, I don't tend to teach that because if you particularly in MET and flight planning, and I think in GenNav as well, the QNH might not be measured at sea level, and the flight computer only works for temperature corrections if the QNH is measured at sea level, because the temperature correction has to be for height, not for altitude, and it only it doesn't account for that. So I tend to teach the formula. Another thing you do have to calculate that can sort of be calculated but shouldn't be calculated on that side of the flight computer is density altitude. Again, it's something that won't come up at PPL, but comes into maybe into GenNav, but also into performance at ATPL level. Don't ever use it. You can use it for an approximation, but it's not accurate enough for the exam. Use the formula for density altitude calculation. So the main thing about the main new things for the flight computer are on the other side. So so far at the PPL level, you've measured your track, or usually you've either been given the track in the exam maybe, or you've measured the track on a chart, and you know the aircraft has. You've then been given the wind direction, the forecast wind direction, and the wind speed. Yeah, and you combine those 4 pieces of information to find the required heading and the likely ground speed. Yeah. And that's probably the only problem you've done on that side of the flight computer. Now, notice, by the way, there are 6 pieces of information here. You've got 3 vectors. I hope you know what a vector is. So a vector is a quantity with both magnitude and direction, as opposed to a scalar, which only has magnitude. Yeah. So we've got, well, wind velocity. We even call this wind velocity, don't we? Velocity is a vector quantity. So speed is a scalar, velocity is a vector. So the wind speed and direction between them give you the wind velocity. And then we've got a mixed one here. That's why this one is a slightly harder problem than some. We've got track and ground speed give the ground vector, and TAS and heading give the air vector. The TAS and heading give the movement of the aircraft through the air, track and ground speed, the movement of the aircraft across the ground. Okay, so what we've got is 3 vectors or 6 pieces of information. And if we know any 4 pieces of information, which as is shown here, it doesn't have to be 2 of the vectors, because this is one of the vectors and half of the other 2 vectors. If you know any 4 pieces of information, you can actually find the other 2. Now, as a general rule, they will give you what the other ones they'll give you are giving you heading, TAS, wind direction, and wind speed, and expect you to work out the track and ground speed. That's actually probably the easiest of these. Yeah. They will also then give you the heading and TAS, track, or sometimes maybe the drift, but often the track. It doesn't matter which they give you, by the way, in that question, and the ground speed, and expect you to work out the wind. Okay, so wind direction and speed. Yeah, so that's the 3rd really common one. There's a 4th that's come up recently. There's a bit of a stupid pain in the ass one, where instead of giving you the track and the TAS, they've given you the track and the ground speed, wind direction and wind speed, and expect you to work out their heading and TAS. Very weird one. And it really just shows that if you do know any of these 4, you can work out the other 2. If you want to know how to do this one, it's not on my main videos, it's on my YouTube channel. there's a video answering an example question like this. So that's not actually very hard. It's almost the same as this, but with a slight adjustment every time you shuffle it. Okay, so there's much more variety. Also, there's the multi-drift wind that I explained to you. That's not a very common question. It's in the it doesn't quite fit with that pattern. It's in the video how to do it. I don't like the fact that they give those, because again, it's obsolete navigation, but they do. Okay, so I just want to finish with a couple of sort of general parts that you need to know about, which help bring the whole GenNav subject together, which is the form of the Earth and the formulas that you're going to need. So you need to know that the Earth is an oblate spheroid. Even that's not quite true, by the way. In my geology degree, we were taught the Earth is slightly pear-shaped. The actual largest diameter of the Earth is slightly south of the equator. So even this isn't quite true, but and you're technically supposed to know that, which is why WGS 84 matters. But you'll and why PZ90 and WGS 84 exist, because there are different geoids which in different parts of the Earth are better representations. Because a geoid is an exact oblate spheroid and the Earth isn't. But for the purpose of GenNav, we'll say the Earth is an oblate spheroid. That's like a sphere slightly squashed in the poles. So it's circular in section around the equator and parallel to the equator, but then it's the largest radius is the equator and the smallest radius is the pole. Yeah. So if you cut it through two meridians, a meridian and its anti-meridian, then you would get a ellipse. Yeah, that's a type of ellipsoid. Has an ellipse got two L's? Oh, ellipsoid. I'm terrible at spelling. Sorry if ellipsoid doesn't have two L's. I can't remember. An ellipsoid means any time you cut through the Earth, it will make an ellipse. A circle is technically just a special type of ellipse. But if it's not parallel to the equator, the cut will show an ellipse that's not a circle. Yeah, if you just take a flat cut anywhere through the Earth, it doesn't actually matter. Because it's an oblate spheroid. Right. For all calculations, we will assume it's a sphere, an exact sphere. Now, that's a really important principle to understand, is that we are assuming the Earth is an exact sphere for all our calculations. The difference isn't huge. It's about 0.3%ish. It's about a third of a percent. So yeah, it's reasonable. It's reasonable to assume it's a sphere for many purposes. Yeah, it does mean what it does mean is we're bringing back what we talked about earlier, that we've got to use non-Euclidean geometry, because the surface of a sphere is not flat, so the geometry doesn't work, and that includes the coordinate system. So if on the surface of a sphere we try and use a coordinate system based on distances, sorry, my drawing isn't any better than my spelling, but okay, so if I took this as the origin of my coordinate system, and so this is my 0, 0, and I wanted to define this location by, well, let's say define x, y as a location. If I went along x across and y up, I would get to this point. But if I went y up and then x across, I get to a completely different point, because my meridians are having to converge closer and closer together, and my east-west distances are shrinking. Yeah. So I would actually, the same two coordinates define two different points. Yeah. So we can't realistically use linear coordinates, distance coordinates. So all our coordinate systems are going to be based on angles. That's why we have latitude and longitude based on angles, not on distances. Yeah. And that's a novelty. That's a thing that you really have to understand. Obviously, the main videos will explain how they are strictly defined. You need to know technically the strict definitions and how you then use them. So that's the form of the Earth and the importance of the form of the Earth. Remember, therefore, we have our coordinate systems. This is what's going to be the most sort of enduring thing. So latitude is north to south, 0 to 90 degrees. I should say 0, 0, because we always put leading zeros in. And longitude is east or west, and that's 0, 0, 0 degrees to 180 degrees east or west. Yeah. And it's always written Latin, then long. I will always write it x degrees, x minutes, north or south, and then y. I should have done this the other way around, shouldn't I? Doesn't matter. Y degrees, y minutes, east or west. You will sometimes see the e and the n and the e before the numbers, and in certain contexts you'll miss out the degrees and minutes characters. Things like flight plans. If you write any lats and longs of flight plans for flight planning, ATS flight plans. So that's why we're really strict with the form. Yeah, if we're doing it to the nearest minute, not the nearest, obviously there are decimals of minutes, which you'll see on Jepson, or you can have seconds again. Then we will always, but if we're doing it to the nearest minute, we'll always be 2 figures of degrees, 2 figures of minutes, even if both are 0 for minutes, for example, or for degrees. 3 figures of degrees, 2 figures of minutes for longitude. Yeah, and then east west. Okay, so you have to be very strict with that. Okay, so that's about the form of the Earth. So then the formulas. So the final thing is about the formulas. There's a stack of formulas based on the change of longitude, change or difference. Now, I will always use change of longitude, and that's most common, but you will sometimes see difference of longitude. They mean the same thing. There is such a thing as difference of latitude. It's not used anywhere near as much. And the calculation is very similar, and it's actually slightly simpler. They will almost always be written Chalong or D long. Yeah, don't worry about that. And it can get confusing. They're mostly trigonometric formulas. We actually use Chalong as well for time calculation, for local mean time calculations, and a little bit of sunrise sunset times. But main calculations here are trigonometric ones, and so we have three-ish. We have 3, but one of them can be split into a few different forms. So there's a convergence formula. And convergence or convergency, they mean the same thing. So I could just run convergency. Is always change of longitude multiplied by some convergence factor. That's where the 4 different formulas comes in. Okay, so the convergence factor can be various things. So for Earth convergence factor is sine of the mean latitude, the sine of the average latitude of the track of the 2 endpoints. Actually, it's the average of the endpoints latitudes. For chart convergency on a polar stereographic chart, for example, convergence factor is just 1. And so convergency on that chart is just Chalong. On a Lambert conformal conic projection chart, which is the most common one, it's what your UK and Jefferson 5.5 mil charts are. It's change of longitude times. There's various forms. Sometimes it will give a sign of the parallel of origin. So the parallel of origin is the central parallel of the projection, and sometimes what will be written as the constant of the code, which is the sign of the parallel of origin. Sometimes you'll even just be given it as the convergence factor. But anyway, overall, convergency has this one formula. It's just this convergence factor changes for different uses of this formula. Okay, and then we have conversion angle, really easily confused. And if you are ever confused by these, think of what the words mean. Sorry for those who don't having anyone watching the video whose first language is not English. Convergency is things pointing towards each other, it's coming together. Yeah, so things converge, they're coming together. And so convergency is the angle between 2 meridians, how they're coming together. Whereas conversion angle, well, this is a conversion. So this is back to our obsolete navigation. This is to convert run lines to great circles or great circles to run lines because of Mercator charts. It happens on a Mercator chart, direct Mercator chart. A straight line is a run line. And so to convert between rhumb and great circles are far more important to navigation. So to convert between the two, we have to use a conversion angle. Hence, I said way back that the only reason it's in the syllabus is because of the history of the nuclear deterrence in the UK, which is kind of weird. And in fact, it's given us half convergency in the learning objective. I'm going to call it half Chalong times sine mean lat. Now, as I said, that's actually half Earth convergency. There is a slightly confusing thing in that they use a pseudo conversion angle. They also, as I said, conversion angle is the angle between rhumb line and a great circle. That's the definition. There's a couple of questions where it's really useful for you to use to find the angle between a rhumb line and a straight line on a chart, which is sort of a pseudo conversion angle. And then you would do half of chart convergence instead of half of Earth convergence. In a lot of cases, by the way, they're the same. Certainly, there's one question on my YouTube channel where I go over one of those exact questions because they're a pain, because they're a bit they're slightly awkward. They're not that bad, but they're slightly awkward. And in that case, actually, Earth convergence and chart convergence are the same because it gives a chart with a parallel of origin at 53 north, and both points are at 53 north, so the mean lat is also 53 north. But anyway, the true formula for the conversion angle is half Chalong times sine mean lat, half Earth convergence. Yeah, so it's easily confused because the convergency sounds a bit like conversion angle, and they both contain Chalong times sine mean lat. Yeah, Earth convergency and conversion angle. But obviously, conversion angle is half the convergency. And so the third major formula that you need is departure. Now, departure, obviously, this is not in the vernacular. This is a term meaning a distance following a parallel, a distance along a parallel. The main subject gives you a lot more detail of this. And this also has Chalong in it. But this is Chalong measured in minutes, not in degrees. Yeah. And this is multiplied by the cosine of the latitude. Now, because it's along a parallel, it's only valid at one latitude, so we don't need mean of the latitude. It's measured in minutes because of the definition of nautical miles, where nautical miles is 1 minute of arc around a great circle on the Earth. Yeah, and you'll see that in detail when you look at the actual video for the main video for this. But this is the formula you will need to know. And it means you can work out things like the length of the 60 north parallel. Yeah. So the equator is actually 21,600 nautical miles long, or 40,000 kilometers, by the way. But the answer comes out in nautical miles, by the way. And this is one thing that's not emphasized always enough, is that this is in nautical miles. So the answer for going all the way around the equator, i.e. at a latitude of 0, where cos of 0 is 1, the Chalong in minutes is 21,600. But if we take 60, where cos of the latitude, cos of 60 turns out to be a half, then the change of longitude all the way around the Earth is going to be 10,800 nautical miles. It means that parallel is half the length of the equator because cosine of 60 is a half. And so, in fact, the length of a parallel is proportional to the cosine of its latitude. Yeah, the length all the way around a parallel. So that's really the meaning of the cos here. We're taking the distance if we were going along the equator, which is the change of longitude in minutes, because the equator is a great circle, and scaling it by the cosine of the latitude. Yeah, and that's something you'll go over. So these formulas are going to be really important to you, and these are things that, and they're important in a way again that's going to be brand new to you. That's why I'm introducing it in this this introduction lesson. Is because these are nothing at all connected to anything you've looked at before, probably in any context. It's just not a thing that on short range navigation ever matters, yeah, ever comes into it. And of course, as I was saying already, actually in real navigation, when you're actually navigating across the world, it's not a thing that's ever going to come into that either. Now you will navigate by great circles, so your bearing will change by convergency. what convergency, the real importance of convergency is not that it's the angle between two meridians, it's that it's how the bearing of a great circle changes as you follow the great circle. And that will happen to you because inertial navigation systems, GPS, inertial reference systems, of course, which are just modern INS, and all radio navigation, in fact, navigates you via great circles. So you will follow great circles all the time. And so convergency will affect your navigation, but you just won't ever actually be calculating it. Yeah, it just comes out of the navigation equipment and you following the navigation equipment. So this is the maths behind what's happening in the navigation systems, or behind or why your track's changing and so on as you fly. It's not a thing you'll ever really have to calculate in the real world. So this is it's not pure maths, but it's more maths than it is navigation. Okay, but it's a new thing and it only applies to long range navigation. Yeah, so I think that's a good introduction to where you're going from PPL level navigation up to ATPL navigation. Yeah. Do you have any questions, TK?
No, I'm okay so far. That's